Titan, the solar system's methane world that mimics Earth. Part 1. Titan's thick orange atmosphere. Titan, Saturn's largest moon, presents itself as an enigmatic sphere cloaked in a perpetual haze, an orange veil that conceals its surface from direct optical observation. This thick, opaque atmosphere is primarily composed of nitrogen, similar to Earth, but with a significant admixture of methane and other hydrocarbons. Unlike our planet's transparent sky, Titan's atmospheric density is formidable, exerting a surface pressure roughly 1.5 times greater than Earth's sea level. This substantial atmospheric blanket plays a crucial role in shaping the Moon's unique climate and geological processes. The distinctive orange hue of Titan's atmosphere arises from the constant photochemical reactions occurring in its upper layers. Ultraviolet radiation from the Sun strikes methane molecules, breaking them apart and initiating a complex series of chemical reactions. These reactions lead to the formation of more complex hydrocarbon aerosols, tiny solid or liquid particles that accumulate and scatter sunlight. This continuous production of organic molecules contributes to the pervasive haze, forming a protective shroud that traps heat and contributes to the Moon's overall thermal balance. This dense, chemically active atmosphere acts as a formidable shield, protecting the surface from the harsh radiation environment of space. It also provides the medium for a fascinating meteorological system, complete with clouds, rain, and surface runoff. The atmospheric composition and dynamics are subjects of intense scientific scrutiny, offering insights into the early Earth and the potential for prebiotic chemistry in extraterrestrial environments. Understanding Titan's atmosphere is the first step in unraveling the mysteries of this distant, Earth-like world. The interaction between sunlight and methane in the upper atmosphere is not merely a cosmetic feature, it is the fundamental driver of Titan's entire organic chemistry. The photolysis of methane generates a cascade of progressively larger hydrocarbon molecules, from ethane to more complex polycyclic aromatic hydrocarbons. These molecules condense and descend through the atmosphere, eventually settling on the surface, contributing to the Moon's rich organic inventory. This continuous atmospheric processing essentially rains organic material onto the surface. This atmospheric blanket is also responsible for maintaining a relatively stable temperature range on Titan's frigid surface. While still incredibly cold by Earth standards, the thick atmosphere prevents extreme temperature fluctuations, making it a more hospitable environment than many other airless bodies in the outer solar system. The greenhouse effect, driven by methane, plays a role in this thermal regulation, demonstrating a surprising parallel with Earth's own climate systems. The visibility within this dense atmosphere is extremely limited, presenting significant challenges for scientific observation. For missions like Cassini-Huygens, specialized instruments were required to penetrate the haze and reveal the hidden world beneath. Radars and infrared sensors became the eyes that allowed humanity to peer through Titan's orange shroud and begin to map its alien landscapes, uncovering a truly remarkable extraterrestrial environment. Part 2. Lakes and Rivers of Liquid Methane. Beneath its opaque orange atmosphere, Titan reveals a landscape sculpted by liquid, yet not water as we know it. Instead, vast lakes, intricate river networks, and expansive seas of liquid methane and ethane dominate large regions of its polar territories. These hydrocarbon bodies are not static, they are dynamic features, subject to meteorological cycles akin to Earth's hydrological system, but operating at cryogenic temperatures. The sheer scale of these liquid reservoirs is astounding, with some lakes rivaling Earth's Great Lakes in size. The existence of stable bodies of liquid on another world in our solar system is a truly profound discovery. Unlike the transient pools found on Mars or the subsurface oceans of icy moons, Titan's lakes and rivers persist on its surface, indicating an ongoing cycle of precipitation, evaporation, and runoff. This makes Titan a unique celestial body, offering a compelling analog for studying planetary processes that once shaped early Earth, albeit with a dramatically different chemistry. Radar observations from the Cassini spacecraft provided the definitive evidence for these liquid features, revealing smooth, dark surfaces that strongly reflect radar waves, consistent with the presence of liquid. Subsequent observations allowed for the mapping of coastlines, islands, and even variations in depth, painting a vivid picture of a world with active fluid dynamics. The images returned were truly alien, showing shorelines carved by waves and channels feeding into larger bodies. The primary components of these liquids are methane and ethane, which exist in a liquid state at Titan's surface temperature of around -179 degrees Celsius. Methane, familiar to us as natural gas, behaves much like water on Earth, forming clouds, raining down, and collecting into surface features. Ethane, a slightly heavier hydrocarbon, also plays a significant role, forming stable mixtures with methane in these liquid bodies. This distinct chemistry defines Titan's unique surface environment. The liquid-filled depressions range from small, isolated ponds to massive seas like Kraken Mare, which is comparable in area to the Caspian Sea on Earth. The depths of these features are still being investigated, but some have been estimated to be tens to hundreds of meters deep. The sheer volume of liquid hydrocarbons present on Titan's surface and potentially subsurface makes it an incredibly rich reservoir of organic compounds, sparking considerable scientific interest. The presence of these liquid bodies underscores the ongoing geological and atmospheric activity on Titan. They are not merely static remnants. They are actively involved in a planetary cycle that shapes the moon's surface and influences its climate. Understanding the dynamics of these methane-ethane lakes and rivers is key to unlocking the secrets of Titan's past, present, and potential future evolution, offering a window into how liquids can sculpt a planetary body. Part 3. Organic Chemistry and Building Blocks of Life. Titan is a natural laboratory for organic chemistry, a world teeming with the very molecules considered fundamental building blocks for life. Its thick, methane-rich atmosphere and liquid hydrocarbon surface provide an ideal environment for complex chemical reactions to occur. Sunlight, cosmic rays, and Saturn's magnetosphere act as energy sources, driving the transformation of simple molecules like methane and nitrogen into a vast array of more intricate organic compounds. This continuous chemical factory makes Titan incredibly compelling. The pervasive orange haze that shrouds Titan is itself evidence of this active organic chemistry, composed of aerosolized hydrocarbons. These particles slowly drift down to the surface, accumulating over geological timescales and contributing to the rich organic deposits that likely cover much of the moon. Scientists have detected a wide variety of organic molecules in Titan's atmosphere and on its surface, including nitriles, which contain carbon-nitrogen bonds, and polycyclic aromatic hydrocarbons, PAHs. The presence of liquid methane and ethane on the surface provides a solvent for these organic molecules, allowing for further chemical interactions and potential polymerization. While water is universally regarded as the solvent for Earth-like life, the possibility of an alternative biochemistry based on liquid hydrocarbons on Titan is a tantalizing prospect. This environment challenges our preconceived notions of where and how life might arise, expanding the potential scope for astrobiological exploration. One of the most exciting aspects of Titan's organic chemistry is the potential for the formation of tholins. These complex reddish-brown organic solids are produced when simple carbon-containing compounds are irradiated by energetic particles, mimicking the conditions in Titan's upper atmosphere. Tholins are thought to be widespread on Titan's surface and within its haze layers, representing a rich source of carbon, nitrogen, and hydrogen that could be raw material for more complex molecules. The detection of vinyl cyanide in Titan's atmosphere is particularly intriguing. This molecule is theorized to be able to form membrane-like structures similar to cell membranes in liquid methane conditions. Such structures, termed azotosomes, could potentially encapsulate and protect organic reactions, a critical step towards the emergence of any form of life. While purely hypothetical, this illustrates the depth of chemical complexity being discovered on Titan. Titan's immense inventory of organic compounds, coupled with the presence of a liquid medium and potential energy sources, positions it as a prime candidate for studying prebiotic chemistry in an extraterrestrial context. It offers a unique window into how complex organic molecules can form and interact in environments vastly different from early Earth. Understanding these processes on Titan can inform our search for life beyond our home planet, expanding our understanding of biological potential. Part 4. The Cassini-Huygens mission's landing. The Cassini-Huygens mission represented a monumental achievement in planetary exploration, culminating in the daring landing of the Huygens probe on Titan's surface on January 14, 2005. After a 7-year journey through the solar system and a release from its Cassini mothership, the Huygens probe embarked on a descent through Titan's thick, hazy atmosphere. This historic event marked the first and only landing ever accomplished on a moon other than our own, providing humanity with its first direct glimpse of this alien world. As Huygens plunged through the orange atmosphere, it meticulously collected a wealth of data, measuring temperature, pressure, and atmospheric composition. Parachutes deployed to slow its descent, allowing for a controlled entry that lasted several hours. During this time, instruments on board captured images of the increasingly detailed landscape below, slowly piercing through the perpetual haze to reveal what lay beneath the enigmatic cloud cover. The images transmitted during the descent were breathtaking, showing intricate drainage channels and what appeared to be a coastline, hinting at a world shaped by liquid. As the probe approached the surface, rocks and pebbles became visible, starkly illuminated by the weak filtered sunlight. The landing site itself, later dubbed Adlai's Fossa, was a relatively flat, dark plain, scattered with what appeared to be icy rocks and a finer-grained material. Upon impact, Huygens survived the landing, continuing to transmit data for over an hour. This extended operation provided invaluable information about the surface properties, including its consistency and composition. The probe's instruments measured the soil to be somewhat like damp sand or clay, likely a mixture of water ice grains and organic precipitates that had settled from the atmosphere. It felt less like a hard rock and more like compressed snow. The success of the Huygens landing was a testament to international collaboration and engineering ingenuity. It proved that a lander could successfully navigate and operate in Titan's challenging environment, providing a proof of concept for future missions. The data from Huygens fundamentally transformed our understanding of Titan, moving it from a theoretical concept to a tangible, explorable world with real surface features and a complex geology. The legacy of the Cassini-Huygens mission is profound. It not only delivered the first direct measurements from Titan's surface, but also opened a new chapter in astrobiology by demonstrating the active nature of organic chemistry on this distant moon. The images and data continue to be analyzed, providing insights that fuel ongoing research and inspire plans for future, more ambitious missions to this truly extraordinary world, expanding our view of planetary diversity. Part 5. The methane cycle compared to Earth's water cycle. Titan operates on a grand scale with a methane cycle that remarkably parallels Earth's water cycle, albeit with dramatically different chemical components and temperatures. On Earth, water evaporates from oceans, forms clouds, precipitates as rain or snow, and flows back into larger bodies of water via rivers, completing a continuous cycle that shapes our planet's climate and geology. Titan exhibits a strikingly similar, yet alien, hydrological system powered by methane. On Titan, liquid methane and ethane serve as the primary volatile fluids. Methane evaporates from the numerous lakes and seas, ascending into the frigid atmosphere. There it condenses to form clouds, which are frequently observed by the Cassini spacecraft, particularly around the moon's poles. These clouds then release their moisture in the form of methane rain, which has been directly detected and inferred from surface changes. This methane precipitation falls onto the surface, carving out intricate river channels in drainage networks that eventually feed back into the liquid hydrocarbon lakes and seas. Radar imagery has revealed extensive fluvial erosion patterns, unmistakable evidence of flowing liquid methane shaping the landscape over geological timescales. This demonstrates a remarkably analogous geomorphological process to those driven by water on Earth. The low temperatures on Titan, roughly -179 degrees Celsius, mean that water ice behaves like rock, forming the solid crust and mountains of the moon. Methane, which is a gas at Earth temperatures, becomes the equivalent of water, existing in all three phases. Solid has ice or frost, liquid in lakes and rivers, and gas in the atmosphere. This temperature inversion fundamentally redefines what constitutes the geological fluid on Titan. Just as Earth's water cycle plays a pivotal role in regulating climate and redistributing heat, Titan's methane cycle is a key driver of its atmospheric dynamics and surface evolution. It influences cloud formation, atmospheric circulation patterns, and the ongoing deposition of organic materials onto the surface. The continuous cycling of methane sculpts the landscape and contributes to the moon's unique weather phenomena. Studying Titan's methane cycle provides an invaluable opportunity to understand fundamental planetary processes in a different chemical context. It allows scientists to test theories about climate, erosion, and volatile transport under extreme conditions, offering insights that can be applied to other planetary bodies, including early Earth. The parallels, despite the chemical differences, highlight universal principles of planetary science, underscoring Titan's importance. Part 6. Icy Mountains and Alien Landscapes. Titan's surface, slowly unveiled by radar in the brief glimpse from the Huygens probe, is a surprisingly diverse and active world, featuring majestic icy mountains, vast sand dunes, and rolling plains. While sculpted by liquid methane, the underlying bedrock of Titan is primarily water ice, which at its cryogenic temperatures behaves like solid rock. This forms the foundation upon which its alien landscapes are built and eroded, creating a truly unique geology. Radar images have revealed extensive mountain ranges, some soaring to several kilometers in height. These mountains are composed of water ice, hardened to the consistency of granite by the extreme cold. They stand as silent sentinels, often bordering the vast methane seas, and are likely formed through tectonic processes, or cryovolcanism, where instead of molten rock, a mixture of water and ammonia erupts to the surface. One of the most striking features of Titan's landscape are the immense equatorial sand dunes. These linear dunes, often hundreds of kilometers long, are not composed of silicate sand like Earth's deserts, but rather of dark, fine-grained organic particles that have settled from the atmosphere. They are shaped by Titan's persistent winds, demonstrating active aeolian wind-driven processes, a fascinating parallel to desert environments on Earth and Mars. Between these prominent features lie expansive plains, often covered with a patchwork of features that hint at past and present liquid activity. These plains may be ancient floodplains or areas where liquid methane has periodically inundated the surface, leaving behind deposits of organic sediments. The surface is a dynamic interface where atmospheric processes meet geological forces, constantly reshaping the terrain. Cryovolcanic structures, thought to be the equivalent of volcanoes on Earth, have also been identified. These features suggest that Titan is geologically active, with internal heat driving the eruption of water-ammonia mixtures that refreeze on the surface, contributing to mountain formation and resurfacing. This internal activity challenges the notion of Titan as a geologically inert body, adding another layer of complexity to its evolution. The alien landscapes of Titan, with their icy mountains, organic dunes, and methane rivers, provide a spectacular canvas for planetary science. They offer a unique opportunity to study geological processes under conditions vastly different from Earth, expanding our understanding of how planetary surfaces evolve. Each new image and data point further illustrates the astonishing diversity of worlds within our own solar system, beckoning future exploration. Part 7. Plans for submarines and drones on Titan. The tantalizing discoveries made by Cassini-Huygens have fueled ambitious plans for future missions to Titan, focusing on novel exploration methods that exploit its unique environment. Among the most exciting concepts are robotic submarines designed to ply its methane seas and aerial drones capable of soaring through its dense atmosphere. These proposed missions aim to delve deeper into Titan's mysteries, seeking direct evidence of its organic chemistry and potential for exotic life. A submarine mission, often conceptualized as, quote, Titan submarine or Oceanus, would be designed to navigate Kraken Mare or Ligaea Mare, Titan's largest liquid hydrocarbon bodies. Such a vehicle would offer unprecedented access to the depths of these alien seas, allowing for direct sampling and analysis of the liquid methane-ethane mixture, as well as any organic sediments on the seafloor. It could explore subsurface currents, measure chemical gradients, and search for evidence of complex organic chemistry. The engineering challenges for a Titan submarine are immense, including operating in cryogenic temperatures, managing buoyancy in liquid methane, and ensuring robust communication with Earth. However, the scientific payoff would be revolutionary, providing a direct understanding of an extraterrestrial ocean that is chemically distinct from any found on Earth or beneath the icy crusts of other outer solar system moons. It would be a true pioneer of deep-sea exploration on another world. Concurrently, a drone mission, exemplified by NASA's Dragonfly concept, would leverage Titan's thick atmosphere and low gravity for aerial exploration. Dragonfly, a rotorcraft lander, is designed to perform multiple flights to various locations across Titan's surface. Its ability to hop between different sites would allow for a broad regional survey, exploring diverse geological features such as sand dunes, impact craters, and potential cryovolcanic terrains. The dense atmosphere of Titan makes aerial flight remarkably efficient. A rotorcraft could fly for extended periods on modest power, covering significantly more ground than a traditional rover. Dragonfly's instruments would analyze surface composition, investigate atmospheric chemistry, and search for complex organic molecules, providing critical context for understanding Titan's habitability and prebiotic chemistry. Its mobility is a game-changer for planetary exploration. Both submarine and drone concepts highlight humanity's sustained ambition to explore Titan in novel and innovative ways. These missions are not just about collecting data, they represent a leap in our ability to interact with and understand other worlds on their own terms. If successful, they would push the boundaries of robotic exploration, unlocking a new era of discovery on one of the solar system's most captivating and enigmatic moons. Part 8. Titan in Science Fiction. Titan's alluring blend of Earth-like features and exotic chemistry has long captured the imagination of science fiction writers, making it a popular setting for tales of future human exploration and alien life. Its thick atmosphere, liquid methane seas, and rich organic chemistry provide a unique backdrop for narratives that explore themes of survival, adaptation, and humanity's place in the cosmos. Titan often serves as a canvas for authors to speculate on alternative biologies and the challenges of colonizing extreme environments. Early science fiction often depicted Titan as a cold, inhospitable wasteland, sometimes with thick, choking smog. However, as scientific understanding of the moon evolved, so too did its portrayal in literature. Once the Cassini-Huygens mission revealed its lakes, rivers, and complex chemistry, the moon transformed into a more vibrant and potentially habitable world in the fictional landscape, inspiring more nuanced and scientifically informed stories. Authors have explored various aspects of Titan's environment. Some stories focus on the logistical challenges of human settlement, depicting domes and underwater habitats designed to protect colonists from the frigid temperatures and methane environment. These narratives often delve into the psychological tolls of living in such an isolated and alien place, far from the sun's warmth and familiar earthly landscapes. Other works of fiction leverage Titan's unique organic chemistry to imagine forms of life radically different from anything found on Earth. Methane-based organisms, silicon-based life, or even sentient beings that exist as energy patterns within the atmosphere have been conceived. These speculative biologies push the boundaries of what we consider life, using Titan as a scientific springboard for imaginative biological possibilities, challenging conventional wisdom. Titan also serves as a setting for adventure stories, with explorers navigating its methane seas in specialized submarines, or flying through its dense atmosphere in adapted aircraft. The moon's immense hazy scale provides a sense of grandeur and isolation, perfect for tales of discovery and peril. The mysteries lurking beneath the orange haze are a constant source of narrative tension and wonder, drawing readers into a truly alien world. From classic pulp stories to hard science fiction novels, Titan has consistently provided a rich tapestry for authors to weave their narratives. It remains a powerful symbol of the unknown and the potential for life beyond Earth, a testament to its enduring appeal as a frontier of both scientific inquiry and creative imagination. Its unique properties will undoubtedly continue to inspire countless future stories. Part 9. Could Titan host exotic life? The question of whether Titan could host life, particularly exotic forms unlike anything found on Earth, is one of the most compelling mysteries in astrobiology. While its surface temperatures are far too cold for liquid water, a fundamental requirement for terrestrial life, Titan's abundance of complex organic chemistry and stable liquid methane-ethane environments open the possibility for an entirely different biochemistry. This potential for non-water-based life challenges our traditional definitions and expands the scope of astrobiological inquiry. Scientists propose that life on Titan, if it exists, would likely utilize liquid methane as its solvent, rather than water. Such organisms would need to adapt to extremely low temperatures and metabolize different chemical energy sources. Hypothetical metabolic pathways involving the reaction of acetylene with hydrogen have been suggested, producing methane as a waste product, a fascinating inversion of earthly processes. The detection of anomalous hydrogen depletion near Titan's surface, combined with the presence of acetylene, initially sparked considerable excitement. While this could be explained by non-biological atmospheric processes, it did raise the tantalizing possibility of methane-based organisms consuming hydrogen and acetylene, much like microbes on Earth consume various gases. This observation underscores the need for direct sampling to confirm any biological activity. Another intriguing concept is the, quote, azotosome, a hypothetical cell membrane analogous to lipid bilayers on Earth, but designed to function in liquid methane. These theoretical structures, possibly formed from vinyl cyanide, could encapsulate and protect the internal chemistry of a Titanian organism. This demonstrates the sophisticated theoretical work being done to imagine how life could arise and thrive in such a radically different environment. The sheer volume of complex organic molecules present on Titan is a powerful indicator of its potential for prebiotic chemistry. These molecules, continually generated in the atmosphere and deposited on the surface, represent a vast library of building blocks that could, under the right conditions, assemble into self-replicating systems. The challenge lies in understanding how these molecules could organize and energize themselves in a non-aqueous environment. While definitive proof of life on Titan remains elusive, the Moon offers an unparalleled natural laboratory for exploring the limits of habitability and the diversity of life. It compels us to broaden our search for extraterrestrial life beyond Earth-like conditions, considering the possibility of entirely novel biologies adapted to extreme and chemically distinct environments. Titan continually pushes the boundaries of our biological imagination. Part 10. Future of Human Exploration on Titan. The prospect of human exploration on Titan, while currently a distant dream, fuels imaginative concepts and long-term planning within the space community. While significant technological hurdles and environmental challenges exist, the unique scientific value and captivating mystery of Titan make it an irresistible target for future human endeavors. Such missions would represent the pinnacle of interplanetary exploration, pushing the boundaries of human endurance and ingenuity. Any human mission to Titan would necessitate extraordinary technological advancements. Habitats would need to be meticulously designed to withstand the cryogenic temperatures, maintain breathable atmospheres, and protect against radiation. Powerful energy sources would be required to sustain life support systems and fuel exploration vehicles. Furthermore, the immense distance from Earth would demand self-sufficiency and robust communication infrastructure, pushing the limits of current space travel. Transportation on Titan itself presents unique opportunities. The dense atmosphere and low gravity would make aerial vehicles, similar to large blimps or dirigibles, incredibly efficient for long-distance travel and surveying. Surface exploration might involve specialized rovers, perhaps designed to float or operate semi-submerged in the methane lakes, offering a truly amphibious mode of planetary exploration that is unique to Titan. The scientific return from a human mission to Titan would be immense. Astronauts could conduct in situ geological and astrobiological studies with a level of flexibility and precision unmatched by robotic probes. They could directly sample surface materials, drill into the icy crust, and even explore the depths of the methane seas, searching for definitive evidence of exotic life or unique chemical processes that are currently beyond our robotic capabilities. Beyond scientific discovery, human presence on Titan would also represent a profound psychological and philosophical milestone. It would demonstrate humanity's capacity to adapt and thrive in environments utterly alien to our home world, pushing the boundaries of what is considered habitable. Such an achievement would inspire future generations and profoundly alter our perception of our place in the universe, marking a new chapter for humanity. While decades, perhaps centuries away, the vision of humans walking on Titan's icy plains, sailing its methane seas, or flying through its orange skies remains a powerful motivator. It embodies the spirit of exploration and the relentless human quest for knowledge. As technology advances and our understanding of Titan grows, the dream of human footsteps on this extraordinary moon will inch closer to reality, transforming science fiction into scientific achievement.